surjective, which means onto. Yeah, it's hilarious. So we've been talking about cardinality, right? Let's talk some more about cardinality. And I want to get to some real sort of punchlines from last time. Last time was a lot of setup about this. Cardinality. This is about measuring the sizes of sets. And a finite set, its cardinality is just a number. You can have a set of 3 things or a set of 5 things. But the cardinality can also be infinite. And as it turns out, there are different sizes of infinite cardinalities. But that's really what we need to talk about today, because actually we haven't seen yet that there's any. That's the surprising thing, that there are different sizes of infinite cardinalities. Here's just a little notation. We're going to write, and you'll see this in the book when we on the homework. A squiggly thing B. This means A and B have the same cardinality. When A and B have the same cardinality. Right? And remember what that means. That means when you think of that, it means they have the same size, the same number of elements. But the definition of cardinality is, I'll just write, i.e. there exists some function A to B, which is a bijection. All right. So last time, for example, really towards the end, we looked at, say, the set of odd numbers. It actually is the same cardinality as the set of even numbers because there is a function that goes one to the other, which is a bijection. So I will say this using the function f of x equals x plus 1, right? That's a bijection. Bijection, remember, means it's one-to-one and onto, or it is injective and surjective. Injective means one-to-one. Surjective means onto, as you know from the viral tweets. I don't think that one was viral, but somehow it got recommended to me. That's not somebody I know. But, all right. By the way, we're not going to get into this really, but I hope that you, in the depths of your memory, remember how to prove that a function is one-to-one or prove that it's onto. This is something you did in your discrete math class probably. And it's probably also something you're going to need to do in your algebra class. Although for this class, we're not really going to talk about onto and one-to-one all that often, but it is important right here. For our purposes, a bijection you can just think of as something which takes one thing in the domain to one thing in the codomain. That's one-to-one. And also, it actually hits everything in the codomain. Nothing gets left out. That's what onto means. All right? Okay, other examples we had something like 1, 2, 3, etc. This is the same cardinality as, I'll write 101, 102, 103, etc. This is because I can use f of x equals x plus 100, and we get the set on the right. Okay? This is strange because the one on the right is actually a subset of the one on the left. The one on the left includes all these elements that are on the right, plus some more, 100 extra elements. But that, so I will just say this is weird but true. I'll say it like this. We can have A is a subset of B with A and B having the same cardinality. All right? Yeah?
Does the cardinality mean the same number of elements?
Right.
One is 100, one is
Yeah, but they're both infinitely many. So one very informal way of saying this, you could say this means that infinity plus 100 equals infinity. That's one interpretation of that. Is that even if you add 100 more things to an infinite set, it's still it's still an infinite set. Right? Now we don't actually. I just wrote that, but actually let's just keep this between you and me. Because this actually this is not a traditional way that people would write these things down. If you want it to be very specific, and we'll get into this a little bit more later on today, but when you're talking about transfinite cardinalities, that is cardinalities which are not finite, so, you wouldn't actually write it this way, infinity. This infinity is kind of a generic symbol, which is usually used for the sort of the hypothetical end of the real number line, but this is not specific enough in that this doesn't actually specify exactly which infinity am I talking about here. So a more accurate way of saying this is you could say something like this: the number of elements of n plus 100 is equal to the number of elements of n. That's more I would be more comfortable putting this on a t-shirt and wearing it around town, something like that, because this is more specific about what we're talking about here. All right, you can have A is a subset of B, but they have the same cardinality. This is only possible if A and B are infinite sets. If they're finite, then that's not possible, because if you have two finite sets and one is a subset of the other, then the subset is automatically smaller. It has fewer things in it, so they're not the same cardinality. All right, how about one more example? Here's another example. How about Z? That's the set of all integers. You know, how about, I'll write it like dot dot dot, minus 2, minus 1, 0, 1, 2, dot dot dot. This is Z. And how about 2Z? This would be all the even integers. Minus 4, minus 2, 0, 2, 4, blah, blah, blah. Right? This is an early candidate for a set which is, perhaps, you might wonder, maybe this set is bigger than n. Because this, this is n, right? It starts somewhere and then it's got a dot, dot, dot. This one don't even start somewhere. It's got dot, dot, dots on both sides. So maybe this one is actually bigger. Turns out it's not. But anyway, these two things, Z and 2Z, do they have the same size? Can you think of a function that goes one to the other, which is a bijection? Yeah? F of x equal 2x, he said. Yeah, I think some of you were thinking that also. This is a bijection. All right, so Z has the same size as 2Z. Yes?
So earlier when you had like a set of half numbers,
Yeah.
like kind of following as we went through this, there will be infinities. Would that be a different infinity? Like why is it still the same?
Yeah, this is, why are these still the same?
Yeah.
Because I can make a bijection between a set with this cardinality and a set with this cardinality. So it is possible to make a set with just the natural numbers, and it's possible to make another set which has those same things plus 100 extra things, and then that can still have a bijection.
So if you couldn't make a function, then that would prove that they're different.
That's right. Yeah, it's all about that. Can such a function exist or not? Yeah.
How is it that the natural numbers are still bigger than
Bigger than this?
Yeah.
They're not bigger, but they're actually the same size,
No.
which is also not obvious, but maybe a little bit more believable. Is it?
That's more believable.
Yeah.
But,
Yeah, they're the same. Actually, that's something that we can, just in a few minutes, I will convince you of that, hopefully. All right. Let's talk some terminology here. I wanted to, all of these sets so far have been sets where I've just been like writing the elements in order, but how about this? How about the closed interval 1 to 1 is the same size as the closed interval minus 100 to 100. This is really not much different from before. Using the function, what function should I use here? To get from, f of x equals 100 times x, right? That takes any number in this range and blows it up by a factor of 100, and what you end up with is this thing over here. All right, and if you cared to, this is an easy example of showing that this function is 1 to 1 and onto. You can, I mean, if you're into calculus, you can draw the graph of this function. It looks something like that, right? I'll make it super thick to cover up that stray marking that I made. And this is 1-to-1. That's a vertical line test. It's also onto. That's kind of like a horizontal line test. So, no. 1-to-1 is the horizontal line test. Onto is just that every y value from minus 100 to 100 gets hit somewhere by that function. Yeah.
So why wouldn't it be the same like x plus 100?
X plus 100. If you take these numbers and multiply them by 100, you get this. If you added 100, it would turn that into like this. Right? That would be adding 100 onto all of those numbers. You add 100 onto -1, you get 99. So that also is a bijection though. So like it's also true that this and this have the same cardinality. All right. How about, this is maybe a little surprising. How about this? 0, 1 versus -1 and 1. Those also are the same cardinality, although it's maybe a little less obvious to think of a function. Can you think of a function that takes one to the other? You want to think of somehow, can you scale this up, maybe move it around or something? Yeah. This is a good idea. If you take the absolute value of this set, you get that set. Yeah. There's something not quite good about that. That is, the absolute value is not 1-to-1. Because, for instance, the absolute value of 1 is the same as the absolute value of -1, which you don't want. That's not a bijection. Yeah. 2x minus 1. Yeah, how did you come up with that? It's
Focus on getting the one. We're trying to get a -1, but I realized blew it up and then shifted.
Yeah, right. Blew it up and then shift it. Yeah, I think if you think of, I would think of these, say, on a picture. The first set is this from 0 to 1, and then the second set is over here from -1 to 1. How do you get from this guy to this guy? Well, first you could multiply everything by 2. That makes it the interval from 0 to 2, and then you shift the whole picture to the left by 1 unit, and you get this from -1 to 1. Yeah, great. So different intervals of different sizes, actually, I say different sizes. This one has width of 2, this one has a width of 1, but in terms of their cardinalities, they are the same cardinality. This is a little weird.
So
Yeah.
so versus like looking at the numbers, like the bounds interval, is it better to think of it in terms of like the size and then use that function?
The
Like,
size,
thinking
meaning like the width of the interval?
Yeah, like thinking of versus manipulating 0, 1. Think of like that whole distance being 2. Does that relate to the other one?
I would say that's a good way to think about it. Yeah, you want. I mean, to me, I think of this as kind of a wide interval of width 2, and I need to somehow squeeze it into this one, which has width only 1. Or actually, really, I was thinking the other way around. If I start with this little one, how do I turn it into this other big one? And the answer is you expand it by a factor of 2, and then you have to do this -1 just to make the endpoints line up. Yeah. Yeah, the cardinality is, well, it's not any finite number, it's infinite. You mean, does it have a name?
Yeah, like
These-
if would you like ask us like what is the cardinality of these
No, because I haven't told you the name of, like, there are these trans-finite things, which are not, they're not ordinary numbers, they have names. So like, there is a name for the size of that. It's, I'm going to get into this later on today, but we're not going to get too into the names though. All right, I had one more interesting example, and then we'll talk some abstraction here. How about you can? So this demonstrates that any two intervals are actually the same cardinality, even if on the line one looks smaller than the other. You can make them the same. They are the same cardinality because you can scale them up and shift them around or whatever. This is a little bit more surprising. It turns out that all of R is the same cardinality as a closed interval also. And just for the convenience of making this function, I'm going to say that. And I'm going to tell you what function. There is a function which takes any real number and turns it into a number between pi over 2 and negative pi over 2. Sorry, that should be an open interval. I didn't mean to make it a closed interval, although it is also the same cardinality with the closed interval, but the function I'm about to say is an open interval. There is a function, a bijection, which takes any real number and turns it into a number in the range minus pi over 2 to pi over 2. And it is f of x equals arctan of x. Remember the arctan? This is the inverse tangent. It looks like this. This is kind of an important function, although it's like very important in some specific fields of engineering. They use arctans, but we are never going to discuss the arctan after this moment right here. But the graph of the arctan function is like this. It has asymptotes there and there, and it does that. All right. And I hope you agree. I mean, you can tell by looking at the picture. This is a bijection. It is onto. That means every y value in this range does actually get a value of the function. The function never hits the endpoints. That's why the interval is open there, not a closed interval. And it's also one-to-one. That's the horizontal line test. Goes through once. All right. So that means that the set of the entire real line is actually the same cardinality as just an interval, which is a little surprising to me. That you can certainly scale one small interval into a bigger interval, but you can even scale a little interval into the entire line, and you still get the same cardinality. All right. Weird but true. There's sort of a whole different realm of like intuition that you have to build up when you're dealing with these kinds of cardinalities. Okay, here's some terminology about this. Yeah.
So does that mean that with those set of real numbers, the interval doesn't matter? Like if any of them?
Yeah, actually, R is the same cardinality as any interval.
Oh.
Because if you don't like this interval, if you want a different interval, say the interval from 5 to 17, then I will just draw you a picture of that function. It looks like this. That's a bijection that goes from the whole real numbers to the interval from 5 to 17. And if you wanted to write a formula for it, it's something like arctan with some weird scaling in it to make it up there. Plus you add something on it to shift it upwards and multiply it by something to squeeze it to the appropriate little window there. All right. Yes. Okay. Terminology here. We say any set A is called. So this is towards the end. Someone asked, like, do these other size of infinities, do they have different names to them? They do have different names to them. This is a very basic kind of name for them. We say any set A is called countably infinite. Countably infinite, or usually we're just going to say countable. When A has the same size as the natural numbers. Countably infinite means that A has the same size as the natural numbers. And this countable, this is really a theorem which we're not going to talk about, but I'll just tell you. This is the smallest size. This is the smallest size of infinite set. All right? The ones which are the same size as the natural numbers. Those are called countably infinite, or just countable. And the other ones, the bigger ones than that, I'll just say if A is infinite, but not the same size as n, then it is uncountable. All right? So countable means infinite, but kind of small, the same size as the natural numbers. And then uncountable means even bigger than the natural numbers. So our goal for today is just to demonstrate that some things are uncountable. So far, every time we've just shown that one thing is the same size as another thing. Some of those things have been countable, some not. So I want to talk about something which is uncountable. Not quite yet. Let me just say, it's actually quite a bit easier in practice to show something is countable, not by making a function, but just by kind of writing out a list. So I'm going to say countable. The reason why this word is used, it means you can make a bijection that goes, say, your set A and the set of natural numbers, goes 1, 2, 3, etc. And if it's countable, what that means is there is some way to arrange the elements in a bijection like this, right? If it's a countable set, countable means that you can sort of line up the elements of your set one by one in an infinite list, all right? If that's possible, then that makes a bijection. If it's possible to line them up next to the natural numbers, then that is a bijection. And so your set A has the same size as the natural numbers. So countable means you can make a bijection. So countable, one thing you could tell your friends at dinner or something, if they ask you what's the difference between a countable and an uncountable, the answer is a countable set is infinite, but it's infinite in a way where you can list off the numbers one after another. I mean, it'll take you forever to actually say the whole list, but you can actually make a list out of them. So countable means infinite, but you can write them in a list. I think this is what the word countable means, like you can kind of count them one after another. 1, 2, 3, etc. Of course, you can't say all of them because there's infinitely many, but you can list them out in a list. All right. Sometimes the same concept is called enumerable, which is a more computer scientists like that word. It means the same thing. You can list the things one after another with some kind of starting point, and then they go one after each other. All right. For example, z, the integers, is countable. Check it out. What I have to do is write down the elements of z in some kind of infinite list. I'm just going to write them down in some sort of pattern. You just have to make sure that you get them all. And it has to start somewhere. We can list them like... Actually, anybody think you can do this? Can you write me a list of the elements of z that actually starts somewhere and then gets all the rest of them in order, not in the ordinary order. They can't go in the ordinary because that doesn't actually start somewhere. How about this? Here's a hint. I don't know if this is a hint. I'm going to start with 0. You got to start somewhere with the integers. Yeah?
1, 0, -1, -2,
Uh-huh. Yeah, this is what I was going to say. And this, I think any of you could have come up with this if you thought about it long enough. Do you agree this is a list which includes all the integers, right? That means that it's countable because you can write the elements one after another. If you really wanted to, you could translate this into some kind of a formula for a function that tells you f of n equals something like -1 to the n times the n over 2 or something like that. It's something like that. But we don't even need to get into that. Just the fact that you wrote this list means, I'll just say we listed them. So z is countable. All right? Great. Any questions about that? Okay, how about this one? How about q? All rational numbers, it turns out, you can write all rational numbers in a list also. Starting somewhere and writing all rational numbers in a list. Check it out. This is considerably less obvious, but once I do it, it's not all that complicated once you see it. 0 I start with. And then I'm going to do this. My goal is to write down every fraction with whole numbers on the top and the bottom, right? That's what we have to do. 0, I begin with 0, which is, that 0 is kind of a special fraction because it doesn't have a unique, at least reduced form, something like that. But anyway, next I'm going to write this. 1/2 minus 1/2, 2 over 1 minus 2 over 1. I'm writing these in little blocks, and each block, this one, the numerator and the denominator sum to 2. And then the next block, and these ones, they sum to 3, right? And next I'm going to write all the possible fractions where the numerator and the denominator, they add up to 4. I mean, ignoring the signs, right? I just take the positive and the negative version of each one. So this next one would be 1 over 3, negative 1 over 3, 2 over 1, sorry, I'm trying to make them add up to 4. 2 over 2 and negative 2 over 2, but actually those I've already listed because they reduce, so I'm going to skip those. Or I could do 3 over 1, negative 3 over 1. I'll say ... So this is a block in which the numerator and denominator sum to 4. All right? Yes?
What about stuff like 2/3?
2/3 is going to be in there. Actually, it'll be in the next block. I will be listing all things where the numerator and denominator add up to 5, and that's where you'll see 2/3. And if you think any fraction will eventually appear in this list, right? Even 22 over 7, that eventually will appear in the block of fractions where the numbers add up to 29. Right? So, our conclusion is, because this is actually a listing which includes every fraction, all possible fractions, so Q is countable. It's hilarious. We know it. All right? This is very strange, because to me Q feels like a much bigger thing than N, just in terms of how Q is dense in the real line, it's packed in to the line, whereas the individual values in N are so sort of spaced out, But it's true in terms of cardinality. N and Q are both countable. All right. Any thoughts about that? Yeah.
So if they're countable, they're going to be the same size, or
Yeah, any two countable sets. When I say countable, it means they are the same size as N. And so, yeah, they're the same size as each other. Yeah. All right. You may get worried about this, like, we're talking about listing the elements. I don't know if you feel like couldn't you just do that with any set? Just write a list. No, I mean, even if it was infinite, like how about R? R is bigger than Q, right? Is it possible to write down a list of all the elements of R? Maybe using some kind of trick like this. I mean, they don't have fractions, but maybe you could use their decimal digits and somehow put them in some kind of a list like that. It's not exactly obvious how to do that, but anyway, I'm here to tell you this is our big example in our remaining 20 minutes. I think we can handle this. R is uncountable, and this was the big discovery by Cantor, which made people interested in this. I think this whole idea of cardinality, if it turns out that every set is countable, that's not terribly interesting. But it turns out there are sets that are not countable, and those are the interesting ones. So I'm going to write this as, let's write this as a theorem. This is first proved by Cantor, like I said, in the 1840s, I think, 1870s, something like that. R is uncountable. And there are a few different ways you can demonstrate this. We're going to, actually I want to show you two different ways. But the first one I want to do is based on the nested intervals property. So what makes this difficult is to show something is countable, all you got to do is write down a big list, right? To show it's uncountable, you have to somehow prove that no possible list can encompass all real numbers. You have to, so what we're going to do is a proof by contradiction. We say, let's imagine that there was a list of all the real numbers, and then we somehow show that that list cannot exist, or maybe that list actually is not exhaustive. It doesn't actually include all the numbers, or maybe that it includes some number twice, or something like that. You have to do this anyway. This is going to be a proof by contradiction. Let's just do it. This is still under the general category in our textbook of consequences of completeness. So we are actually going to have to use the completeness axiom here, and we're going to use it in the form of the nested intervals property. But anyway, let's just get to the setup. I'm going to say, for the sake of a contradiction, let's assume that R is countable. I.e., what that means is that R as a set can be written as a list of elements. So I'll just assume that it's like that, right? One after another. This is what countable means. x1, x2, x3, x4. All right? And then, like I said, we're going to use the nested interval property, but actually what the punchline of the whole theorem is that we'll end up showing that this list is not exhaustive. That is to say, i.e., there exists some real number not in the list. That's going to be our contradiction at the end. We assume that you have a whole list which includes every real number, and the contradiction will be we're actually going to find a number, an individual number that's not on the list. All right. Okay. Let's see if we can do this. It's actually the idea of doing the proof is not something that is easy to think of, but it makes sense well enough when you see it presented to you. So I'm gonna try and draw a little sort of example here with points. Let's imagine my points go like x1 is here, x2 is here. Let's say it will help if you draw exactly the same picture that I'm drawing here, although this is meant to be just like a representative example here, etc. The setup is we have imagined somehow that you could just write out every real number in a list one after another. Now they don't go in order in this list, so as I've drawn them, I have x1 is over here, and then x2, and then x3 is up here, and x4 is over here, and x5 is back over here. They would have to jump back around in some ways just to cover the whole line. They're going to have to, in fact, jump around in a crazy manner, which actually is not possible at all. But if we're assuming the real numbers can be written as a list, they have some arrangement like this. And I'm going to turn this scenario into a bunch of closed nested intervals. All right, and here's the strategy. So we make intervals. I'm going to say make nested closed intervals. So that, let's say, I'll write it like this: in excludes xn. That's the whole idea of the proof. And this is actually how Cantor originally did this. Make nested closed intervals one after another so that in excludes xn. Let's just see what does that actually look like on this picture. On this picture, I1 is supposed to be a nested, well, it's not nested with anything because it's the first one, but I1 is supposed to be a closed interval which excludes x1. And it could be anything. For the sake of this picture, maybe I will write it. I'm going to try to, I know you can't do this on your paper, but I'm just going to try and line things up here. Let's say I1 is an interval like that, maybe. All right? It's any closed interval which excludes x1. That's the important thing here, is that x1 is there, being left out of this interval. All right? And then I2 is another closed interval. It has to be nested. Sorry, I wrote in, that should say I1. That's the first one. You just choose any interval which excludes x1, all right? Any closed interval. And then I2 is supposed to be a subset of that, because it has to be nested, which also excludes x2. So when I draw I2, x2 is right here. So I make it smaller so that it does not include x2. And I might as well leave the other input the same. So here's x2 now being omitted. This is I2. x2 is left out of I2. And you keep on shrinking the interval like that, so that in each step, you shrink it down so that it omits whatever point it is you're talking about. So for the next step, I need to shrink this interval down so that it omits x3. And I will do that. There's actually many ways you could do that, but maybe I'll do it this way. This one is I3, which excludes x3, which is right there, right? And I keep on shrinking the business like that. The next one down needs to exclude x4. Now sometimes as you're doing this, you'll notice the point is already excluded, like this point, this interval here already excludes x4. Then I would just keep it the same. That's fine. So this is I4, which excludes x4, which was already being excluded anyway. All right, next I shrink down. I5 needs to exclude x5, so maybe I'll shrink it like this, right? Where I left out x5 gets left out over here. Come on. Right. X4 was all the way over here, of course. This is how we do it. This is how we are going to build each interval. All right? And you can continue this as long as you like. Okay? These things are constructed to have this property. So xn is not in In for every n, right? All right. They are closed intervals just because I said so, and they're nested because that's how we build them. We build each one by shrinking the previous one, so that makes them nested. And specifically, they are made to have this property. xn is not in In. All right? But what does the nested interval property mean? Anyone remember? But the nip says, what does it say? Yeah. The intersection of it all is not empty. So I will just write that formally here. Intersection n equals 1 to infinity of In is not empty. What that means is there is some point which is in all of these intervals. There's some real number in all of them. All right. So there exists x, a real number, such that x is in In for every n, right? Okay, but here's where the contradiction arises. But xn is not in In, right? So this x here, I'll just write it this way. X is not equal to x of n. That's because xn is not in In, but x is in In, right? So they can't be the same number. So this number x, this like magical number that you got from the nested intervals, it is not equal to any of the xn's that are in the list. Anybody see why that's a contradiction? Yeah. The x is actually in all of the intervals here, and it's a real number. Yeah?
Is it that, like, xn is in, like, the original big set, but x has to be outside of that?
Yeah.
It's not that even.
Yeah. So really, what I'm saying here is x is different from all the xn's, right? But remember, we began the xn's make up all real numbers. That's the contradiction, right? The list is supposed to include every single number, but in the end we found a number, another real number, which is different from everything in the list. So it means your list did not actually include every real number. That's the contradiction. I would say it's because these individual numbers, we begin by assuming that every single real number is on the list somewhere, but then these can shrink and shrink and shrink to exclude all of those, and because of the nested interval property, there's still going to be something left, and that thing which is left is not part of the list at all. Yeah. And so the conclusion is, it means it's not possible to make a list, because no matter what's on the list, you can always find something that's not on the list, right? And this apparently is a property of the real numbers, but not of the rational numbers, because you can actually make a list of the rational numbers, which really does include everything, but you can't with the reals. Yeah. Yeah, like these ones which I drew on the picture, there are many other ways that you could have drawn them. Is that what you mean? In a way which avoids these points in the same way?
I just mean like,
Yeah.
like if the list goes on forever in both directions, could you just draw nested intervals around each?
Well, the intervals are supposed to exclude these points one by one. These points, they go on forever in both directions. I would say, I'm not sure this is answering your question. Most of the time, you're going to be using the same interval after itself, because most of the points are out here. I'm not sure what I'm answering the question properly. It sounds like you're saying you want to grow the intervals from one step to the next, but I'm not trying to do that, because I'm trying to use the nested interval property, which is about intervals which are shrinking. So you need to structure the argument so that the intervals get smaller every time.
Like how can you say that like we're excluding a point if like we just make the intervals bigger?
Well, I'm not. It's up to me to define what the intervals are, right? So I'm just saying I'm going to make them nested and closed so that they get smaller every time and they exclude these points every time. Yeah. Sorry for the unsatisfying answer. I'm not sure. Yeah. All right, so let me say, we got a few minutes left here. I didn't quite finish writing. X is different from all the xn's, and this contradicts the fact that R equals x1, x2, etc., right? Because we began by assuming that every real number is on the list. We then found a number which is not on the list. That's the contradiction, all right? We got 6 minutes. I'm going to try to give you this is a slightly less formal version of the proof, which doesn't use the nested interval property, but this one actually you could explain to all of your friends, I think. You can tell your little brother about it. So this here was the original proof by Cantor in, I believe, like the 1870s, but Cantor actually came up with what I think he considered to be a better proof, and which was very influential. This sort of cuter, it's definitely a cuter proof. So in the 1890s, this became sort of a famous proof. He called it, I don't know if he called it this, but we today call it the Cantor's Diagonalization proof, or the diagonal argument, or something like that, and you'll see why it's called this. And this is the one that you could explain to your friends. So, to get a contradiction, we begin the same way. To get a contradiction, assume that R can be written as a bunch of things listed one after another. All right? And we'll find this, to trigger the contradiction, we'll find some real number not in the list. And this proof involves decimal expansion. So let's write it all out, write them as decimals. And this part of the proof, I'm just going to sort of make up some decimal numbers at random. Let's say for some reason x1 is 1, just the number 1, 1.0000, etc. Right? That certainly better appear on the list somewhere. And then maybe let's say x2 is pi, 3.14159 something something. Let's say x3 is 8.675309, etc. This is one of my favorite numbers. If you know, you know. Let's say x4 is, how about 7.3 repeating? It really doesn't matter what these numbers are, but I'm just trying to make some stuff up, right? You just have to imagine when you're talking to your kid brother, you're trying to convince them it's not possible to write down the real numbers in a big list, okay? Because if you thought you had a list, you could write the decimal digits like this. And now I'm going to find, how about this? I'll just put 0 on the list. That better be somewhere on the list, right? I can find a number that's not anywhere on your list, even though your list goes on forever, right? Here's a number not on the list. And I don't mean it just doesn't appear among the ones you wrote down so far. I mean, this number which I'm about to write is definitely not anywhere on the list. Anybody see how to do this? This is not an easy idea, but once you see it, it's kind of a beautiful proof because it will suddenly become clear to you when you see the strategy for building the number that's not on the list. Here's a hint. It's called the diagonal argument. I'm going to do this. I don't know if this will impress you. My number, which is not on the list. Anybody see where this is going?
Yeah.
Yeah? What? Can you give me a number that does not appear on the list? Add them up to create a new number. Yeah, I'm not sure about add them up, although, yeah, you're going to look at those values, somehow change them around maybe to create a new number, which you can guarantee is nowhere on this list. Anybody have an idea?
So, I should question that.
Yeah.
If this list contains every number technically, how could you make a number that way that's not on the list?
Well, that's the contradiction. I mean, the true fact of the matter is there can be no list which contains every real number. And that's what we're trying to demonstrate here. If you think there is such a thing as a list which contains every real number, I'm going to show you actually it doesn't, because there's a number that's not on the list. It's about, you can see how to do it? I'm going to modify those circled digits. How about I'll just add 1 to each of those digits. And if it's a 9, I'll roll it over to 0 or something. All right? I get 2 point, it doesn't really matter where the decimal point goes, but 2.2841, etc. How do you know that number's nowhere on the list? Well, this number, this is different from xn in digit n, right? Because of the way this sort of diagonal pattern works, this number that I wrote here is different from x1 in the first digit. It's different from x2 in the second digit. It's different from x3 in the third digit, and so on. That means this number is different from everything in the list. You like that? I don't know. I like it.
So is it that you have to take a digit from every number, or is it like, just the way that like decimals are, like, there's no way that you could have every, I don't know, I'm just confused.
You have to look.
That number that you make from the diagonals isn't in the list.
It's not in the list.
But I feel like if, like, say that the list has every number, how is it not in the list?
Well, this is a proof by contradiction. So, sorry, I scrolled not enough.
How does it show that it's not in the list just by like being made up of list?
Yeah, it's because for like if you think maybe it is in the list, then maybe, I don't know it, but this number maybe equals, say, x sub 9981, right? Actually, it can't equal that number because of the way these diagonals worked. I would have built this number to be different from the digit, the 9981th digit. That position, I changed that number by one digit when I made this one.
Leaving the number with its position.
Yeah, this
Okay.
number here is specifically created to be different in every position from every one of those numbers. Yeah. All right, I think.